When we construct a thermometer, like the alcohol thermometer that you use, the uncalibrated thermometer, to do the first experiment, the column length of the alcohol doesn't really look like this, but the point is that it's not a linear graph. It might go up, then down, then up. The slope might change. It might curve, or it might increase a little faster, then a little slower, then a little faster. By definition, air doesn't, or ideal gases don't do that. Ideal gases stay linear, and that's our standard of linearity. For an alcohol thermometer, we don't have linearity, and if we're going to calibrate a thermometer, we can't just calibrate it at 2 points. We have to calibrate it at a variety of points, usually using a gas thermometer that measures temperature in terms of pressure, to obtain the actual curve of the thing, and we mark the thermometer accordingly. Now, over a small range, that graph is pretty much linear. So over a limited temperature range, we do have pretty good linearity. Over the range from 0 to 100 Celsius, an alcohol thermometer is pretty linear. It's satisfactorily linear for most applications and most experiments. So we say over limited temperature range, the column length is nearly linear, so linear scale works fine. There are other things that we use other than the column length of alcohol or mercury or some other element or some other substance. We can use thermocouples and other infrared temperature measuring devices and so forth. So it wouldn't necessarily be column length against temperature, but whatever we measure against temperature is going to have some curvature, isn't always going to be linear, and we need to keep that in mind. Ask ourselves, what are the limits on the linearity that we think we have? Now, looking at the situation where we put a rock into the water. Okay, if we have a mass, and we're just symbolizing the situation, we've already analyzed the situation numerically. But we put a mass M2 of rock at temperature T2 into water. What's going to happen? Well, if T2 is greater than T1, that is, the temperature of the rock is greater than the temperature T1 of the water. Water has mass M1, temperature T1. Then we're going to come to a higher temperature, and the water is going to come to a higher temperature. The rock is going to lose thermal energy, and the water is going to gain thermal energy. We're going to end up with a mass M2 of rock and a mass M1 of water, assuming we don't lose any mass here. And they'll be at some common temperature TF. We're going to leave the rock in the water till they come to a temperature TF. And we're going to assume for right now that the system is closed. That is, that there's no thermal energy transfer between the environment and the system. So that we have a temperature change T1 of the water, delta T1. The delta T1 is just going to be the final temperature minus T1. And that's the temperature change of the water. The temperature change of the rock will be delta T2, which is the final temperature, minus the initial temperature of the rock, which is T2. In a closed system, again, where there's no energy gain or loss from the environment, we have conservation of energy. The change in the thermal energy contained in the rock, which is delta Q2, plus the change delta Q1 in the thermal energy of the water has to be 0, which of course means that these thermal energy changes are equal and opposite. Now, delta Q2, as we've experienced, we multiply C2, which is the number of calories per joule per Celsius degree required to raise the temperature of the rock. That's a number of calories per joule per Celsius degree. It's a number of joules per gram per Celsius degree, or number of joules per kilogram per Celsius degree to raise the rock's temperature, multiplied by the mass of the rock, multiplied by its temperature change. And that should be clear from the experiments. It should be very clear how we get this. Okay, and then delta Q1 is the same thing for the water. The 4.18 joules or 4.19 joules per gram Celsius degree multiplied by the number of grams of water multiplied by the temperature change of the water. These two quantities obey this conservation of energy law. So that we have C2M2 delta T2 plus C1M1 delta T1 equals 0. Delta T2 is TF minus T2, delta T1 is TF minus T1. So here's our conservation of energy equation for the situation where we put the rock or the steel washer or whatever it is into the water. How do we deal with that equation? Well, that depends, of course, on what it is we know and what we're trying to find. In our experiment, try to get zoomed back to the right point here. In our first experiment, we measured the mass M1, the mass M2, and the final and the initial temperature of the water. And I didn't list it, but we also measured temperature T2, the temperature, the initial temperature of the rock, or at least we assumed that that temperature was equal to the temperature of the water in which the rock was boiling. The rock wasn't boiling, the water was boiling. Okay, so we had this information and we were given C1. Where does that put us? Well, the underlying quantities, M2, TF, T2, M1, TF again, and T1 are all things that we either measured or were given. So it made it easy to find C2. We just solved this equation for C2. Now at this stage, the equation should make perfect sense as a conservation of energy equation. These expressions should make sense because they just summarize in symbols what you've done in the process of completing the experiment. In other situations, we might know C1 and C2 and find masses or temperatures. Any one of these quantities could be unknown. We might know the two temperatures and the two masses and the two specific heats and try to find the final temperature. That's a fairly common type of calculation. But in every case, we have this situation, we have this equation, or some equation that's similar to it, modified from it in some way.